Hi guys, I hope you are having a good day. So let's continue our lesson. This time we have a new topic. So this is on errors in chemical analysis. So the learning outcomes are the following. Number one, to identify different types of error in quantitative analysis. Number two, to calculate measures of random error. Number three, to differentiate precision and accuracy and compare the associated statistical tools, and to evaluate basic analytical data by applying statistical tests like the mean, standard deviation, variance, RUST, and the t-tests. So let's start. There is no chemical analysis that is completely free of errors or uncertainties. Errors are basically inherent in any analysis. We can, however, minimize these errors within an acceptable level of accuracy. So in this topic, we will understand the nature of experimental errors and their effects in a chemical analysis. So let us illustrate this using the figure shown in the slide. So here, a student analyzed 6 equal portions of an aqueous solution that contain exactly 20.00 ppm of iron 3 in exactly the same manner. The results range from as low as 19.4 to as high as 20.3. The average is calculated to be 19.8. So these errors or uncertainties produce a scatter of results you see in the figure. As what we've said earlier, we can never completely eliminate these errors, so the true value for any quantity is always unknown. However, we can evaluate the magnitude of these errors and estimate the reliability of our experimental data. Generally, reliability can be assessed in several ways. Maybe experiments can be done to reveal the presence of these errors, or we can calibrate our equipment and glassware, and this can enhance the quality of our data. And of course, we can use the statistics. Chemists or chemical analysts carry out the analytical procedure in replicates. So when we say replicates, these are samples of about the same size that are carried out through an analysis in exactly the same way. So usually around 2 to 5 replicates that are done. So just like in the given example, so we have 1, 2, 3, 6, 6 replicates. The results of these replicates are seldom the same. So if you look at, again, our example, we have 19.4, 19.5, 0.6, 0.8, 20.1, and 20.3. And so, a central or best value is used for the set. So this central value is more reliable than any of the individual results. Either the mean or the median may serve as the central value for a set of replicated measurements. So going back to our given example, we calculate the average or the mean to be 19.8. So again, you know this already. So I think you have covered this in your senior high. And then the median is just the middle result when the replicate data are arranged, maybe in increasing or decreasing order. So if the number of replicates is an odd number, so we only have one value. So we only have one middle result. If it's an even number, just like in our example here, so we just get the average of the two middle values. So in here, so we get the average of 19.6 and 19.8, and that's 19.7. Okay. Another important aspect in describing the experimental data is the precision. So this refers to the reproducibility of measurements In other words, the closeness of replicated measurements. To describe the precision, we can use the standard deviation, variance, and coefficient of variation. All of these three are a function of the deviation from the mean, or the d sub I. Another one is the accuracy. So this indicates the closeness of the measurement to the true or accepted value. And oftentimes, this is expressed by the error. However, we can determine the accuracy. We can never determine the accuracy exactly, because the true value can never be known exactly. So what we do, we use an accepted value instead. So we use the absolute error or the relative error to describe the accuracy of the measurement. Absolute error is denoted by the uppercase letter E, and it is calculated by the formula given in the slide. So xi minus xt, where xi is the given experimental data, and the xt is the true or accepted value. In the analysis described earlier, the accepted value is 20 ppm, because that's the target. On the other hand, the absolute error is expressed as a percent or as a ppt, or parts per thousand. If the value is negative, just like in our example, it means that the experimental result is actually smaller than the accepted value. So again, precision is the closeness between repeated measurements. Accuracy is the closeness of a measurement to the true value. And these are illustrated in the figures shown in the slide. We consider the bull's eye of the dart as the true or accepted value. So we can have values or replicated measurements having low precision, and at the same time low accuracy, as what's shown in the figure in the top left. So this figure. Okay, so this illustrates low accuracy and at the same time low precision. Okay. In the bottom left, so this illustrates a low precision, but pretty much each measurement are not that far from the bullseye. So we can say that the accuracy is quite high. In here, so very precise. You look at the replicated measurements. They're very close to each other, but they are very far from the bullseye, from the center. So this illustrates low accuracy. Of course, the last example, this is our considered the ideal results. It has the results have very high accuracy, very close to all of the measurements are very close to the center, and relative to each other, we can say that the results have very high precision. Okay, so let's proceed to the types of error. Earlier, we were talking about accuracy and precision, and these two mean differently, as we all know. And so we cannot assume that if we know the answer precisely, we also know it accurately. So we will illustrate this using the given example, and we will soon understand that chemical analysis are actually affected by at least two types of errors. So please look at the figure on the screen. So this actually summarizes the results of the determination determination of nitrogen. In two pure compounds, we have benzyl isothiourea hydrochloride and nicotinic acid. So analyst 1 and 2 for the benzyl compound, and analyst 3 and 4 for the nicotinic acid. The dots that you see here, the dots show the absolute errors of replicate results obtained by these 4 analysts. So let's look at each of these analysts. So analyst 1 obtained relatively, you look at the dots, analyst 1 obtained relatively very high precision and high accuracy. Let's proceed to analyst 2. So as you can see, the dots are quite scattered. So analyst 2 had poor precision but good accuracy. The absolute error is not that high. Let's look at the results of analyst 3. So actually, the precision is very good. So very close to each other. But we can say that there is significant error in the numerical average of the data. In the results of analyst 4, we can say that both the precision and the accuracy are actually poor. So looking at these results of these 4 analysts, we can say that the chemical analysis are actually affected by at least 2 types of errors. So one type, called random or indeterminate error, causes the data to be scattered more or less symmetrically around a mean value. So if you look at the given figure again, and you would notice that the scatter in the data, thus the random error for analyst 1 and 3 is significantly less than that for analysts 2 and 4 in terms of how the dots are scattered. So analyst 1 and 3, it's not that scattered, and then compared to analyst 2 and 4. So we can say that analyst 1 and 3 have less random error. The second type of error is called the systematic or the determinate error. This causes the mean of a set of data to differ from the accepted value. So for example, again, the results of analysts 1 and 2, we can say the results have very little systematic error. But the data of analysts 3 and 4 show systematic errors of about 0.7. So the analyst 3 here, so that's around 0.7. And negative 1.2, no? Negative 1.2 here. So if you look at the average. So in general, a systematic error causes the results in a series of replicate measurements to be all high or all low. Okay, so again, the results of analyst 1 and 2 have little systematic error. Okay, but analysts 3 and 4, the errors range from negative 0.7 in here, and then to negative 1.2% nitrogen. The third type of error is actually a gross error. So gross errors differ from indeterminate and determinate errors. They usually occur only occasionally and are often very large and may cause a result to be either high or low. And these gross errors may lead to what we call as outliers. So these outliers, these results, they appear to differ very greatly from all the other data. So we call this as the outlier. We can use stat tests to determine if the data point is actually an outlier or not. So that ends for this part. So before you proceed to the next subtopic, please uh, do and accomplish the activity for this subtopic.